Alright, so we're going to finish off this unit talking about Kepler's laws. Kepler worked a lot with Mars. That was his main focus. And he developed these three laws of planetary motion, which we still use today. So there's this guy, Tycho Brahe, that I've mentioned before. You can see he has a giant nose. That's because he drinks a lot. But besides drinking, he was also an astronomer. And he had this observatory on this island where him and his cohorts would measure the positions of every known thing in the currently known thing in the solar system and all the stars and stuff. So he did a lot of measurements for Mercury, Venus, Mars, Jupiter, and Saturn, and our moon. And here comes Count Dracula. Johann Kepler. He was Austrian, and he was interested in how the planets moved. So he went to Tycho to get these measurements. Tycho's kind of a jerk and didn't want to give them to him. He tried to corrupt Kepler because Kepler was a very pious, devout guy. Tried to get him to drink and do bad things. But Kepler stuck to his guns, and eventually Tycho died. And right before he died, he gave him all his measurements finally. So at that time, many astronomers believed that the planets orbit around the sun in perfect circles. But Tycho's measurements for Mars didn't fit a circle. So everybody thought we just went around in a perfect circle. But the measurements were slightly off. Didn't predict where they should be using the math very well. So no circles. We don't like circles. And so instead, the mathematician Kepler found that the orbit of Mars fits an ellipse the best. An ellipse, a squashed circle kind of looking thing. And I'll have a picture of it right here for you. A lovely ellipse. So what is an ellipse? If you remember from geometry class, the kind of egg-shaped things. And has two foci instead of one central focus. So a circle is just a circle with one focus in the center. But this ellipse here has two focuses. So what these focuses mean is you can draw circles, and that's going to be the center of one. Sorry, my circles are kind of lame. So this focus should be over here. Let me erase that. So it has two focuses, two foci, however you want to say it, instead of a circle which only has one. Yeah, I guess I did draw it on there. Here, computer's usually better. And then here is our planet going around this ellipse. And here's our sun at one of the foci. Pretty sun. And there's nothing over here at the other one. Just kind of an imaginary dot in space. So we're going around this. Sun's at one foci. Nothing is at the other guy. That is the first law of planetary motion. That the planets orbit the sun in an elliptical form. So ellipse also has a major axis, which is going to be its longest. If we cut it in half lengthwise, the longest way is going to be the major axis. It's going to have a minor axis, which we cut it in half the other way. That's the minor axis. And it's going to have a semi-major axis, which is half of its major. And these are the two words you're going to have to know for your quiz. Perihelion. So perihelion is when our planet is closest to the sun. It's sun's at this focus, the planet's right here. And conversely, and here's the definition for it, when Mars or any other planet is closest to the sun. It's at perihelion. So there's our little picture of Mars. And opposite of perihelion is aphelion, which is when the planet is furthest away from the sun as it can be. So perihelion and aphelion. Now it's time for a second law of planetary motion. So Kepler also found that Mars changed speed as it orbited the sun. So it moved faster when it was closer to the sun. So whenever it was at perihelion, it was moving the fastest. and one was that aphelion is moving the slowest. So further away you get, the slower you move, and you start getting closer and you start speeding up. And this is because of gravity and all that other fun stuff. So what his second law of planetary motion says is that areas A and B, these two pink shaded areas, there's area A, here's area B, swept out by a line from the sun. So Mars starts here, ends here, and then it's going to start here and end here, with the sun as the endpoint over here. They're equal over the same amount of time. So if this guy took 1 month, I can't draw an N, 1 month, and this time it took, time it took from go to here is 1 month, and time it took to go to here is also 1 month. That means these two pink shaded areas will be equal. So if another month was like from here to here, we drew our little slice of pie. These are the weirdest slices of pie ever. I'd be kind of angry if I got one of these for pumpkin pie during Thanksgiving. But if this took 1 month to go from here to here, then this area would be equal to this area and this area. So equal amounts of time yield equal amounts of area. So Kepler found a relationship between the time it took a planet to go completely around the sun, which we know is a period because we're orbiting around the sun, and we call this a sidereal year, and the average distance from the sun, so the semi-major axis. So we're talking about the semi-major axis and how long it takes to go around the period. And he developed his third law of planetary motion. So T1 squared, so this period right here, the entire period, divided by T2 squared, so how long it took this planet to go around the sun, is going to equal the semi-major axis cubed divided by this one's semi-major axis cubed. And you can rearrange this all different kinds of ways. You can have like T1 squared R squared cubed equals T2 squared R1 cubed. Rearrange this all different kinds of ways. You can get all, R's on one side, T's on one side, T over R's, all that fun stuff. So Earth's sidereal year and distance both equal 1. So the average distance, so we took like Earth to be like the base. So Earth's period and Earth's distance is going to end up being 1. And the average distance from the Earth to the Sun is called 1 AU, 1 astronomical unit. So if we have T2 being our information for Earth, anything with a 2 subscript as our information for Earth, and our basis is 1, because we measure everything from the Earth because we're very egotistical, then we just end up with this guy over here for a planet. So its period squared is going to equal its radius cubed, basically. So when we compare the orbits of planets, we find that T squared and R cubed are essentially equal. So for Venus, these guys are pretty close to each other. For Mars, pretty close. Jupiter, pretty close. Kind of interesting that it works out that way. Nature is very elegant. So Kepler's laws apply to any celestial body orbiting another celestial body. So we can use these problems for stuff orbiting Jupiter, we can use stuff orbiting Saturn, we can apply it anywhere, like any orbiting stuff. So any planet around our sun, the moon around our Earth, satellites around the Earth, International Space Station goes around the Earth, Saturn's rings, Neptune's rings, all that stuff. Anything that orbits something else, we can use Kepler's laws. So later, Newton, he took Kepler's laws and he used them to actually confirm his law of gravitation. And if it wasn't for Mars and its complicated travels across the night sky, Kepler may not have derived his laws of planetary motion. Newton might never had his foundation for his law of universal gravitation. So thank you, Mars, for being a cool planet. So the red planet Mars is forever linked to our understanding of the solar system and one of the 4 basic forces of nature, being gravity. And it's also, they've had it in movies and stuff. Sometimes they're cool. Most of the times they stink. That's it, short guy. Enjoy.